All right, ready to dive into some fluid mechanics.
Let's do it.
We've got this really cool chapter from a textbook all about it. And,
Yeah.
well, we're going to try to break it down, whether you're an
Okay.
engineer or just someone who's curious about how things work.
Exactly.
Imagine you're designing like a massive dam or
Yeah.
a really sleek airplane.
Right.
You're not just going to, start building and hope for the best,
Yeah,
right?
definitely not. No. That's where models are so important.
That's right. So that's what we're looking at today. This deep dive is all about dimensional analysis, similitude, and modeling in fluid mechanics.
Yeah, it's a pretty powerful set of tools, like having a crystal ball,
Yeah.
almost,
I like that.
for fluid mechanics.
So let's start with the basics. Why are models so important in fluid mechanics? Why can't we just, use equations and figure things out theoretically?
Well, I mean, you can to a point, but a lot of these real-world problems are just way too complex. We just can't solve them just with math. That's where experimentation comes in, and that often means using scaled-down models.
Right. So it's like a test run
Yeah, exactly.
before you build the real thing.
Yeah. Think of it like, you wouldn't launch a brand new airplane without testing it in a wind tunnel.
Right. So it's all about being safe and also saving money in the long run.
Exactly. Catch those problems early.
Okay, now let's get into the nitty-gritty. Dimensional analysis.
Yeah.
Your source material calls it a trash compactor of information.
Yeah. I love that analogy.
So what does that even mean?
So picture this. You've got a ton of data about some fluid flow problem, right? Pipe diameter, velocity, viscosity, density, it just goes on and on.
Right, it can get overwhelming.
It can. But dimensional analysis helps us take all that information and squish it down into these nice, manageable pieces. We call them dimensionless groups.
So instead of solving the problem directly, it's more about just kind of organizing all the information.
Yeah. Yeah, and the cool thing is you can then apply the results from, say, a model to a full-scale prototype, even if they are different sizes. It's like a universal translator for fluids.
Now, that is powerful. It sounds like something that could have prevented a lot of engineering mishaps that we've seen throughout history.
Absolutely.
Speaking of which, your source material mentions something called the Buckingham Pi theorem. What is that all about?
Well, the Buckingham Pi theorem basically tells us how many of these dimensionless groups, these pi terms, we need to describe a particular problem.
Oh, okay.
Like engineers used it to figure out the thrust of early jet engines before they were even built.
That's incredible. But how do we even find these pi terms in the first place?
It's actually a pretty systematic process. There's this thing called the method of repeating variables.
Okay.
It involves identifying those key variables, like flow rate, viscosity, and then expressing them in these basic dimensions like mass, length, and time.
So it's like translating everything into a common language.
Exactly. And then we use some, algebra to combine those variables into dimensionless pi terms. And these pi terms, they really capture the core relationships between the variables.
Okay, so we've identified the variables, translated them, and then used them to make these pi terms. What happens then?
Then you got to make sure those pi terms are truly dimensionless. That's crucial, like a quality control check, because if you even have a small error, it can throw off your entire analysis.
Gotcha. So like building a house, you got to make sure
the foundation is strong.
It's all level.
Exactly. So once we have our pi terms all set, we can express the relationship between them in a nice, simple equation. And this equation is it's the essence of the problem boiled down.
So we've distilled all that complexity into just a single formula.
That's it. And that formula can help us understand the problem better, but also design experiments to actually test out what we think will happen.
I'm starting to really see the beauty of this whole approach.
Yeah, it's pretty elegant.
Like a secret decoder ring for fluid mechanics.
Exactly. And that brings us to some of the the most famous words in this language, the common dimensionless groups, like the VIPs of fluid mechanics.
Okay, tell me about these VIPs. I'm intrigued.
Well, you've probably heard of some of them, like the Reynolds number, the Froude number, and the Mach number.
Yes.
Each one has its own unique story, and they're all key players in how fluids behave.
So like a team of specialists.
Yeah, you could say that.
Each with their own expertise.
Exactly. So the Reynolds number, that one helps us understand if a flow is smooth and orderly, like honey dripping off a spoon, or if it's chaotic and unpredictable, like a rushing river.
Oh, okay, I see.
It's named after Osborne Reynolds, who was a pioneer in fluid mechanics.
That makes sense. And what about the Froude number? What's its specialty?
The Froude number. That one comes into play when gravity's a big factor, like ships moving through water
Oh.
or water flowing over a dam spillway. Named after William Froude, he was a naval architect, studied ship design. And then we got the Mach number, that's the speed demon.
The Mach number.
Yes.
I know that one. That's all about, like, breaking the sound barrier.
Right, supersonic jets. Named after Ernst Mach, he was a physicist and philosopher who studied sound and motion.
It's amazing how each of these groups helps us understand how forces work together in a flow.
Mm.
And it lets us compare flows of different scales, which is super important when we're building models.
Exactly.
It's like having a Rosetta Stone
It is.
for the language of flow.
That's a great way to put it.
So speaking of models, let's talk about how these dimensionless groups help us design models that that actually work, that reflect real-world behavior. It's like creating a mini-universe
It is,
where all the same laws apply.
It's not just about shrinking everything down proportionally, though.
Right, so it's not just about making a miniature version.
Right. You have to think about things like velocity, viscosity, and the density of the fluid to make sure the model really reflects what the prototype will do. You know, it's going to be the same physics playing out, just on a smaller stage.
So it's like setting up a miniature stage play.
Yeah.
Where the actors are different, but they still have to follow the script.
Yeah, exactly. And to capture certain things about the flow, sometimes we have to create these distorted models where we don't scale down every dimension the same way.
Distorted models. That sounds counterintuitive.
Yeah.
Why would you want to make a model that's not, like, perfectly to scale?
Well, I mean, sometimes you have to. Imagine you're building a model of a river
Okay.
to see how the water flows around bridge piers.
Okay.
If you scale down every dimension equally, the model river might be so shallow that you have these big surface tension effects that wouldn't happen in the real river.
Oh, right.
So it's a trade-off. You got to balance keeping the shape similar with dealing with things like surface tension.
So in that river example, you might make the model river deeper than it should be,
Yeah.
just to avoid those surface tension problems.
Yeah, exactly. That way you can still study the flow patterns.
Oh, I see. So it's like a puzzle, figuring out how to best represent the problem.
Yeah, it is. And by understanding these ideas, you know, dimensional analysis, similitude, engineers can build these incredibly accurate models that help us design safer and more efficient things.
Wow. We've covered so much the theory behind dimensional analysis, how to design models, and it's really like we've unlocked a secret code to understanding how fluids flow.
That's a great way to put it.
And it's amazing how this can be used for so many different problems, from figuring out efficient pipelines to predicting how air moves around buildings.
Right, the applications are endless.
It's amazing.
Yeah.
But before we get too carried away, I'm curious about some specific examples, some case studies that show how powerful this stuff really is. You mentioned, things from tiny particles all the way up to giant structures.
Oh yeah, there are some really cool ones.
Well, let's dive into those. But first, let's take a little break to process all this amazing info. We'll be right back to explore these case studies and see the world of fluid mechanics in action. Welcome back. Before the break, we talked about all that theory, but I'm ready to see how it works in the real world, with some examples.
Yeah, for sure.
You mentioned some case studies about tiny particles and giant structures.
Right.
Let's start small. What about that example of a spherical particle falling through, like, a thick fluid?
Oh yeah, that's a classic example of Stokes flow. That's where the fluid's viscosity is, like the dominant factor. Like, picture a tiny ball bearing sinking through honey. It's going so slow.
Okay, I can picture that.
And, you could try to figure out the drag force on that particle with a bunch of complicated equations,
Right.
but dimensional analysis makes it way simpler.
So it's like, instead of trying to juggle all those variables,
Yeah.
we can use dimensional analysis to make the problem smaller and easier to handle.
Exactly. And in this case, it turns out that the drag is directly proportional to the particle's velocity and diameter and the fluid's viscosity.
Okay.
It's pretty straightforward, and it can be used in things like sedimentation,
Oh, interesting.
where understanding how particles settle is super important.
So we can learn about something complex,
Yeah.
like how sediment forms over time,
Mm-hmm.
just by looking at a ball bearing in honey. That's amazing.
It is.
Okay, now let's scale things up.
Yeah.
What about those giant structures?
Yeah.
You mentioned an example about predicting, vortex shedding frequency.
Yes. That's a really interesting one. So basically, when fluid flows past an object,
Right.
it can create these swirling vortices that
Yeah.
detach and move downstream. And those vortices they can cause vibrations,
Oh, I see where this is going.
which can be a really big deal for structures, especially bridges.
Right, like that famous bridge collapse, the Galloping Gertie.
Yeah, exactly. The Tacoma Narrows Bridge.
It's a reminder that these forces
Oh, yeah.
are powerful and we got to understand.
Yeah, right. We've learned a lot since then, thankfully. Now we use models to study these things so we can design structures that can handle those vibrations.
Okay, so going back to that bridge component example,
Yeah.
do they, like, build a tiny version of the whole bridge to test it?
Not usually, no. They'll often just focus on the specific parts that are most likely to have those vortex shedding problems.
Okay.
So, for example, they might build a scaled-down model of a bridge pier
Okay.
and then test it out in a water tunnel. That way they can study those frequencies in a controlled environment.
So it's like zooming in
Yeah.
on the parts that could
Well,
cause trouble.
And by making sure the Reynolds number, you remember we talked about that?
Yeah.
By making sure that's the same between the model and the real bridge component, engineers can predict pretty accurately how those vortices are going to behave.
And that helps them design bridges that can actually withstand those forces.
Exactly.
It's really amazing. It makes me think about all the other structures out there, you know, buildings, airplanes, wind turbines.
Oh, yeah, it applies to all of them.
Where these same principles are at play.
Right. Dimensional analysis and modeling are everywhere. They're used in all sorts of things, pipelines, race cars.
It's like we have this master key
Mm-hmm.
that unlocks the secrets of how things move through fluids.
That's a great way to think about it.
Mm.
And speaking of unlocking secrets, you know how we were talking about interpreting those dimensionless groups as energy ratios?
Yeah, that really caught my attention.
Like we've been looking at these groups one way,
Right.
and now we have a whole new perspective.
So we can think of them not just as comparing forces, but also how energy
Exactly.
is distributed in the flow.
Exactly. It's like looking at a painting under different lighting conditions.
Okay.
You might see things you didn't notice before.
I love that analogy.
Yeah.
So what new insights could we get from this energy perspective?
Well, thinking of, say, the Reynolds number as an energy ratio could help us understand that transition between smooth and chaotic flow,
Yeah.
you know, laminar versus turbulent.
Right.
It might tell us something about how the energy is distributed and dissipates in different types of flows.
That's fascinating. It's like we have a whole new way of seeing these dimensionless groups, which opens up a ton of possibility.
It really does.
I'm eager to hear more, but I know we need to wrap things up soon. Anything else you want to highlight?
One more thing. You remember how we talked about the Buckingham Pi theorem helping engineers figure out the thrust of those early jet engines?
Yeah, that was a great example.
Well, there's another dimensionless group that was super important for those jet engines, the thrust coefficient.
Okay, tell me more.
It basically relates the thrust to things like the air density, the engine's diameter, and the velocity of the air going into the engine.
So it's kind of like a performance score for the engine.
Exactly. And just like those other dimensionless groups, it lets engineers compare different engine designs, even if they're totally different sizes.
It's another example of how this can bring order to these complex engineering problems.
Right. It's all about making sense of the chaos.
So from little particles to giant structures to powerful engines,
It's all connected.
these dimensionless groups are really the unsung heroes of fluid mechanics.
I'd say so, definitely. They're the key to understanding, predicting, and controlling fluids.
Well, this has been an amazing deep dive. We've gone from basic dimensional analysis to designing models and even looked at how these dimensionless groups are like energy ratios.
It's been fun. I hope you've got a new appreciation for how cool fluid mechanics is.
Oh, definitely.
Yeah.
It's amazing how something that seems simple, like water flowing in a pipe,
Right.
can be explained by these really powerful principles.
And this is just the beginning. There's so much more to discover.
I know, this has definitely sparked my curiosity. Where should I go from here if I want to learn more?
The reference section in your source material is a great place to start. Lots of books and articles there. You can also find tons of stuff online, websites, podcasts, even YouTube videos.
So many resources to explore.
Yep. And it's all out there for anyone who wants to learn, whether you're a student or just curious about the world.
So to wrap up, what's the most important thing you want our listeners to take away from this deep dive?
I think it's to remember how powerful models are and the principles behind them. It doesn't matter if it's a tiny particle or a giant airplane, the same laws of physics are at work. And by understanding those laws, we can really understand the world around us.
That's beautifully put.